Yeah.
Okay, so then we come to the next talk, which will be as well a combination of two papers. That makes it a four-liner for me to read, right? Quantum Secure Non-Malleable Randomness Encoder and its applications, that's the first one, and Split State Non-Malleable Codes and Secret Sharing Schemes for Quantum Messages. The speaker is Naresh Goud Boddu. So.
Hi, everyone. So happy to be here, and today I'll be talking about Quantum Secure Non-Malleable Randomness Encoder and its applications, and Split State Non-Malleable Codes and Secret Sharing Schemes. So let's try to understand what each of the term means in the title, maybe by the end of the 20-minute session. Okay, I'm going to cover in three parts: introduction, where I introduce the primitives, and the second part where I'll be stating our results and some nice open questions. And let me begin with introduction straight away. Non-malleable codes are primitives which are useful to protect against some tamperings in certain way. It is that when we decode the initial message M at the end of the decoder, what we need is that we want either the decoded message to look like the original message or something which is unrelated or independent of M. So that is in sentences, but more mathematically what we have is that M prime is convex combination of two things. The first distribution is the initial distribution of the message, and the second distribution is something that depends only on the adversaries. So how hard is it to construct such codes? So for a general adversary function family, it is known that we cannot construct such non-malleable codes. So people have studied non-malleable codes when adversary has some certain restrictions. One of the most well-studied adversary model is so-called split state model, and here the ciphertext contains of two parts in the two split state model. More generally, if you have T splits, then ciphertext will be of T parts, and here adversary is allowed to tamper the ciphertext independently on each of the splits. And of course, we want nice encoding and decoding schemes with rate as close to 1 as possible. Right. So let's come to the second primitive, which is non-malleable randomness encoder. So what non-malleable randomness encoder NMRE is that it's a further relaxation on non-malleable codes in the following sense. For non-malleable codes, we get a message M and we want to output X and Y, which are non-malleable encodings of it. But for NMRE, it takes in as input some random input as uniform randomness, and it is going to output us three registers. First one being random message, and the other two parts having the non-malleable encoding of the message. So in this picture, as you can see, the encoder non-malleable randomness encoder NMRE takes in as input uniform bits, and it gives us three parts. The first one being supposedly the uniform message M, and the other two parts on which we expect adversary to tamper. And here again the guarantee that we want is that that M and M prime to look as either the same or uncorrelated with each other. And now we mentioned in the title of the talk, it's about quantum secure and again quantum non-malleable codes. So let me begin with what split state adversary mean in the quantum setting. What we mean is that when adversary is tampering the splits, adversary has access to unbounded entanglement and is allowed to do some quantum operations. And this model is introduced in Agarwal, Boddu and Jain work, and we will be working in this one. And now what we mean by quantum secure NMRE, which is the first part of the talk, is that when adversary is restricted to quantum operations with unbounded entanglement, we want the NMRE security to hold M prime should look like convex combination of two things. M prime is same as M, and M prime looks like M in tensor with M prime. And analogously, like how we define quantum secure NMRE, one can also define quantum secure non-malleable codes. And let's come to prior work, which has been done rigorously over the last decade, especially in the non-malleable codes, that starting from inverse polynomial rates to constant rate, which is achieved recently in two-split state model. The only work that is known in the quantum setting is the work of ABJ, which constructed inverse polynomial rate non-malleable codes against quantum adversaries. So now let's come to non-malleable randomness encoder. What has been done previously is that very nice work by KOS, Kanukurti, Obertu, and Shekhar, which constructed two-split NMRE, which is rate optimal, rate half, and which is against classical adversaries, and it is known to be quantum secure. And right, so why do people construct this non-malleable codes and non-malleable randomness encoders? Is that it has some nice applications to non-malleable secret sharing, non-malleable commitment schemes, and secure message transmission, non-malleable signatures. So, right. And now let me delve into the second part, which is stating our results formally. That the first result being, we provide a construction of rate half two-split non-malleable randomness encoder, which is supposedly arguably simpler than the construction given in KOS, and it is rate optimal, and it is shown to be quantum secure. So to elaborate, as the previous rate half two-split NMRE construction uses predominantly 3 crypto primitives, which are message authentication codes, seeded extractor, and poor rate non-malleable codes. And our quantum secure NMRE consists of only one crypto primitive, which is two-source non-malleable extractor. And so crucial observation being that we observe that non-malleable randomness encoder can be constructed using any two-source non-malleable extractor. So, and what do we know? Any quantum secure two-source non-malleable extractors? Yes, we do. In the earlier work of BJK21, they have constructed a two-source non-malleable extractor, which is quantum secure. If we just instantiate the two-source non-malleable extractor, we get NMRE, which is quantum secure, but rate 1/8. So in this work, we work in their framework and optimize parameters. Takes bit of work to reduce this rate from 1/8 to increase the rate from 1/8 to 1/2. And now let me come to define what quantum non-malleable codes means. That let's say we have an input message M, and M hat being any purification of M. So for quantum messages, this is what we mean by think that the final output state along with the M hat register should look like the original MM hat and the decoupling that happens between M hat and M, which can be seen here. So this is our definition of quantum non-malleable codes for input quantum messages. Now, before dwelling into our construction of quantum non-malleable code, it's nicer to see what has been studied in a much simpler setting with shade key that is being present at encoder and decoder. So it is this quantum non-malleability with shade key is considered in earlier work, and they proved that any two design unitary function family can give such a non-malleable code property. And let's now try to use our NMRE construction to construct 3-split quantum non-malleable code. So as you can see in the previous slide, that if encoder and decoder had access to this R, they could have used the two design unitaries to achieve non-malleability. So how about we try to protect this key R using the NMRE itself in 2 splits, and then we use this key to use 2 designs on to protect the message. So formally, we use 2 splits to protect the key R, and we use the 3rd split to protect the message using 2 design unitaries. So this proof goes over in 2 cases. The first case when the two splits where we used to protect R ensure the adversary ensures that R is equal to R prime. In this case, very nice properties of two design unitaries, which is polymixing and decoupling properties, imply the non-malleable code security. And the second case is when adversary changes even a slightly one bit in the two splits, then what we have is the much stronger thing that R prime will look like, R looks like uniform and independent of R prime. And this is a property, very nice property that we get these two cases from two source non-malleable extractors. And once we have this in the second case, then decoupling property of two design unitaries give us the desired non-malleable security. Right. And now how about quantum secure non-malleable codes? By quantum secure we mean encoding and decoder, everything is classical, only the adversary is quantum. And the same similar construction replacing two design unitaries by pairwise independent permutations give us quantum secure non-malleable codes. And the thing is that the rate difference comes only from the difference in the sizes of two design unitaries and pairwise independent permutations. So this gives us rate 1/5 3-split quantum secure non-malleable codes. And now our goal was to construct 2-split quantum non-malleable codes. And how about first trying to combine two splits and call it store in the first splits and the third split being independent. And taking this approach will lead us to problems. The first problem being that now when we cannot assume that X and Y are protected against adversary by 2nmx. The reason being that to tamper Y, we are giving additional information, which is register G, which carries information on R. So the security of NMR no longer holds. So how about, but noting that the encoding that we are doing this is a unitary, and if message M is uniform to begin with, then Z carries no information about R anymore. So we proceed to work this argument for a uniform message M, and this alone is not sufficient. What we need additionally is augmented property of two source non-malleable extractor. And in addition, we use transpose trick for a uniform message with canonical purification M hat. And combining all three, we can construct 2-split quantum non-malleable code for uniform input message, and which is rate 1/11. But the key thing is that message is no longer worst case. In the 2-split case, we are able to achieve only when the message is uniform. And similarly, replacing two design unitaries by pairwise independent permutation, we get rate 1/5 2-split quantum secure non-malleable codes. So right, so quantum NMCs for in the uniform input case can be thought of as we are trying to protect 1/2 of maximally entangled state against this split state tamperings. This is the punchline of this theorem in the quantum setting. Right. So now let's go to our application of non-malleable codes, which is non-malleable secret sharing. And right. So non-malleable secret sharing is defined in Goel and Kumar work. And let's say we have a secret sharing scheme. Let's call it threshold secret sharing scheme, T out of P. What we mean is that the number of parties are P, and only T of them, at least T of them should come together to decrypt, to reconstruct the original message M. And at most T-1 parties hold no information, theoretically hold no information about M. That is what T out of P secret sharing scheme means. And suppose now we allow the adversary to tamper P shares to primes, which we call. And now when we reconstruct, let's call the message to be M prime. And again, we call an secret sharing scheme to be non-malleable when we have a security of this form. MM prime should look as convex combination of original message and decoupling with the original message M. Right. And there is a compiler which is given in Goel and Kumar work, which uses 2-split non-malleable codes in a black box way. And additionally, they use the secret share T out of P secret sharing scheme and 2 out of P leakage resilient secret sharing schemes. So what we mean by leakage resilient secret sharing scheme is adversary to also get some leakages on all the shares of the P, and even then adversary from point of view the original message M is hidden information theoretically, right? So what is the candidate threshold NMSS scheme? It is simply first use 2-split non-malleable code to get 2 shares L and R, then apply T out of P secret sharing scheme on L to get P shares, and apply 2 out of P leakage resilient secret sharing scheme on R to get P R, and then set the ith share to be Li and Ri. And the reduction from threshold NMSS to 2-split non-malleable codes goes in 2 steps. The first step is we need to show that tampering of R to R prime must be performed independent of R. That's what we mean by split state tamperings, right? And similarly, tampering of L to L prime must be performed independent of R. So seeing that R to R prime tampering independence of R is simpler because R prime depends only on R1 prime and R2 prime, because R is encoded into 2 out of P leakage resilient scheme, and which R1 prime and R2 prime further depend on L1, L2. But L1, L2 holds no information about L. And the second part where the argument gets a bit tricky is that showing L to L prime is independence of R. Here we need viewing L primes as leakages on R i's. We get such a property. And so the leakage resilient secret sharing scheme has to be tailored to the case that to see Li prime size has to be much smaller than Ri's, and that inhibits the rate. And overall, combining these two, they construct this three random variables LER such that using E they can tamper L to L prime, using R they can tamper R to R prime. So now let's try to see this reduction in the quantum setting. Is that the first step goes analogous to the classical setting, and the second setting is second step being, again we were able to argue that L to L prime can be independent of R, not just leakage resilient, but what we call augmented leakage resilient secret sharing schemes. And overall, these two we expect to construct such a classical argument, but we cannot, in the quantum setting, we cannot hope to identify such LL prime, ERR prime satisfying these two. So this is an inherent quantum problem that pops up when we argue quantum security. And before elaborating on this problem, let me conclude that combining all three, and we get replacing secret sharing with quantum secret sharing, leakage resilient with augmented leakage resilient, then GK protocol gives us quantum non-malleable secret sharing scheme. So let me just conclude with saying the difficulty that usually comes. Suppose we have XEY 3 registers, let's say they are independent, even they form a Markov chain. Then let's say adversary tampers EX to EXX prime, EY to EYY prime. Then in the classical setting, one can see that XX prime, EYY prime forms a Markov chain. But when the adversary is quantum, then the above Markov chain may not be true. And this is one of the key difficulties that is handled in earlier works also when they considered quantum security of non-malleable extractors. Right. So let me conclude with some open questions. Note that we only constructed 2-split non-malleable cores in the average case setting. So how about for worst case? And of course, we considered only individual joint tamperings, and how about against much stronger adversary tampering models? And how about if we considered computationally bounded adversaries? So this brings me to my final slide. Yeah, if any questions?
Thank you.